you may call, if it is disconnected, you may call in my mobile number. So Narendra, are you there? Narendra? Okay, I think he's not there. Anyone, just please be attentive. So yesterday we are discussing about full custom. I don't know. Yeah. Uh, Yesterday we are discussing about full custom design flow, right? So in the design flow, what we discussed that in the beginning you should have a specification of your chip or IC, whatever you talk about it, right? Specifications in terms of say first order specifications, you may get area, speed, and power, and then other second order specifications you will get it like what is the clock. I mean, speed means that is clock period, and what is should be the jitter, what should be the input delay, output delay, right? So what type of power, like dynamic power, static power. So all these powers, all the specifications you should have mentioned during your this stage. You have to find out your specification based on your applications. So this is one first step you have to find out. You have to freeze it at the beginning. So in addition to this physical specifications, you have to find out what is the functionality based on your applications. You have to find out what type of operations you require on your chip, silicon chip. So functionality is a very important that you have to find out, and based on this functionality, you have to get your circuit topology. You have to get your circuit topology. Circuit topology means that you have to get your circuit design part based on base topology. You may get a various type of topologies. Maybe it is existing, or you maybe have a innovative circuit. You can have your new circuit. You can or you can have an existing circuit topology. You have to choose depending upon your applications. So once the circuit is part is done, then yesterday as I was talking about, you have to go with your circuit simulation, circuit simulation, and verification. Circuit simulation and verifications. How I will move forward. Okay. Yeah. So you have to go with the circuit simulation and verifications. Once it is done, that you are satisfied that your functionality is working in this level, circuit level, then you have to move to your next step, that is called physical design. That is called your uh, physical design, physical, or that is called a layout design. This step is a physical or layout design step. Next step you have to move where you have to design various layers of your devices, or that is transistors, and its interconnections, that is your meta layers. So that is the why it is called physical. Because all the layers have its will have its own dimensions. What should be the length, and what should be the width, and what's the depth of your circuit. Okay, I mean that layers of your transistors and the interconnections, and that is called your circuit. Okay, so physical or layout design of your circuit. Right. So what is the schematic? You got it. So you satisfy, okay, the circuit is working. This is circuit topology means that is a schematic design. Okay, circuit topology means that is your schematic design. This is your schematic design. So based on the schematic design, you have to design your physical or layout designs. Once it is done, the physical layout you have completed, we will go on detail of this layout design. But in the brief, I am describing what is the full step, so that each step we will go in detail. So in the physical or layout design, after physical and layout design, you have to go and you have to verify, right? Every step you have to do either verifications or validations. So you have to go with the physical layout design verifications. So this is called a physical verification. Next step, you have to go with your physical verifications. Physical verifications. So in the physical verification, as I told that in this stage you have to do the various physical verifications such as DRC, LVS, ERC, signal integrity, antenna check, okay, density check. So all these, checks you have to do depending on the core or chip level verifications. You have to do it. Once it is done, then physical design. Once it is done, then it is verified. Then you have to move to the next step. That is your if it is a core level, then you have to integrate your core integration with pad integration, because you are going with the circuit design. So now next step you have to go with the integration of pad. Okay, integration of the pad means that is your IO pad. This is called your integration with the IO pad. So once it is a IO pad integrated, then you have to do again the chip level verifications. Chip level verifications. Chip level verification. Verification. Okay. So once chip level verification will be done, then it is okay. Then you have to do the next step, generate GDS to file, that is called a in a technical terminology, it is called a GDS. GDS is extension of your layout design. So that layout design will be exported or generated as a GDS. GDS is nothing but your geometric data stream. GDS is nothing geometrical data stream. Geometrical data stream, GDS. Okay, I mean this stream, this bit, this is these are the bit files. Okay, these are the bit files of your layout. Bit files of your layout design. I mean, it contains the coordinates of each layer. Or it contains the coordinates of each layer, and it will stream as a bit file, and that is called a and saved as a file. Your file name dot GDS. GDS2. That is called name as GDS2. GDS stands for geometrical data stream. And sometimes some people talk about this is a graphical data stream. Graphical data stream. Instead of geometrical, they talk about the graphical data stream. But most of the people, they talk about the very technical appropriate word is phrase is geometrical data stream. That is saved as a file dot GDS2 or chip dot. So if your file name is your chip, then chip dot GDS2. Okay, GDS2. So this way you can generate your GDS2, and this step is called your tape out. Tape out means you are taping out your design, or you are generating your GDS2 in this case. Okay, and once this GDS2 will you generate it, then it will go to a foundry. It will send to a foundry. The design steps is completed over here. Then this tape out, what is the generate GDS2 you have received, that will go to the fabrication steps. It will go to the fabrication step. In the fabrication step, I am just completing your design step. In the fabrication step, what will happen? It will receive your GDS2. Let me write it that fabrication step. Fabrication step. What it does? It will receive the GDS2. Receive GDS2. Okay, receive GDS2 means that what is your layer informations, it will be sent to your fabrication people foundry, where the chip fabrication will take place. Okay, so before fabrications, what it does, it will receive the GDS2. From the GDS2, it will generate a mask generation. Next step is called your mask generations. So in the mask generation, what it does, that it will generate the uh, um, uh, layer mask for each layer. It will generate a mask for each layer. Suppose say for example, you have a source. Talk about the MOSFET device. I am sure you have studied the MOSFETs. So this is a source, this is a drain, and this is a gate. So if you look at that, particularly the source region, gate region, and drain region, so you will have a, suppose if you look at the three-dimensional or three-dimensional view of your devices, then you will have a source, right? So it have a source, it have it is doped with suppose it is a n type material, and NMOS. If it is NMOS, right? So source and drain is a n plus. If you having n plus diffusion region, this is n plus diffusion region, this is n plus diffusion region. Okay, and this is your p type substrate. P type substrate, this is your p type substrate. P-type substrate, and you will have a gate region. This is your polysilicon, right? Polysilicon layer, polysilicon part, and this gate oxide, this region, the gate region, you will get your gate oxide. Okay, gate oxide. Basically, this is a silicon dioxide. It is a, the properties of the gate oxide is your very thin, good dielectric material. Okay, silicon dioxide material. The property of the gate oxide, I'm sure you might have knowing this one. So gate oxide is a gate oxide is nothing but gate oxide. Gate oxide is nothing but very thin, good quality, good quality, good quality dielectric silicon dioxide material, right? So that will be deposited, in this source, and sorry, in this gate oxide region, and above that you will have a polysilicon layer, and below that you will get your channel, okay, which is your p-type, right? With the this is a p-type. So so what it does here, if you look at the 3D of your NMOS um, device, you have a some length and width and depth of the source region, where n plus diffusion, basically the boron material will be deposited here in this region, source and drain region. And of course, this p-type substrate means this is a wafer, which where the p-type material will be deposited, uh, uh, and this source this source and drain region is a boron material will be deposited, you know boron or phosphorus, that is n-type, to create n plus diffusion layer. So it has a, so it is having its own length and width and depth. Here also length and width and depth, and the channel will have its also own length and width and depth, and the gate oxide also will have a its length and width and depth, and the polysilicon material also will have its length, width and depth. So each layer, if you look at all layers, will have its own size in terms of length and width and depth. So if you look at the in top view, in the top view you will get your say suppose in top view, if you look at that, this region will be one is a source, another will be a drain, and in between the region you will get your this is source and drain. In between source and drain you will get your channel, you will get your gate oxide, and you can put your you will get your polysilicon material, right? Polysilicon. So same area where you can cover, if you choose the area of a channel, this is your area channel. In between source and drain, I am looking where I am looking for. This is a, suppose this channel region. So make it is a rectangular type. So channel region, this area will be, you can realize your channel, you can realize your gate oxide region, you can get your polysilicon material, you can realize your or deposit your polysilicon material. So here you can get your raw raw devices, many simple devices, you can realize it. But when you will go for its connections, like interconnections to get your circuit, then you have to deposit, you have to do the interconnections, right? So you have to get your metal layers to be deposited. So if you want to take a metal layer or interconnections, then you have to put a metal layer, or that is called a contact layer, in source region and drain regions, and which will be connect your source region to with your say suppose this is a metal layer, metal, and this is also metal, you want to get connected to the other circuit, then this metal and source has to be get connected through a contact, and that is called your active contact. This is called your active contact. Okay, this is also is called your active contact. So once it is done your active contact, then then it will get connected to the metal wire. So we will come again to the detail of this layout design, but we understand that we need all these layers, we need for the your fabricating your devices and circuits. So to deposit the material in these regions, you have to select, you have to this is a total device regions. So you have to select a particular region for a particular particular type of either it could be a source, or it can be a drain, or it can be a channel, or it could be a gate oxide, it could be. So you have to select, you have to select a particular region, right? So if you want to deposit a some material in a particular regions, say particular you want to deposit a boron material in a particular regions here and here, so you have to select it, right? So suppose this is a total wafer, and you want to select, this is the source and this is a drain, where you have to deposit your boron material, where you have to deposit your boron material. So this is a whole wafer in the whole. I'm talking about only single device, right? So if you look at when like a number of devices you have to put into a single wafer in a single base, then you have to all the source and drains you have to of a similar type you have to select first, and you have to deposit on the boron material on those selected portions where you have to create your source and drain of a particular n type or p type, right? So there you have to deposit, you have to select it. I means what you have to do in this region, if I will suppose this is simple device, a single device I'm taking, where I need one source, one drain. So this where I have to put the boron material, these two places. So what I have to do, I have to select these regions where I have to deposit, where I have to deposit the boron material, right? I have to deposit the boron material, right? So this is the fabrication process you have to do. Then how to select this region? And when you will put the boron material, it should not be, it should not be deposited in other part of your this base region, okay, substrate region, right? It should not be deposited. Selectively, it should be deposited here. So then what you have to do, you have to mask other regions. I mean, you have to cover off other regions, and you have to selectively open this region only where you can deposit your boron material, where you can deposit your boron material, right? So accordingly you have to. So when you will cover it up means that you have to mask. You have to mask to cover a particular regions. You have to mask to open up your particular regions. So that means that you have to generate a mask. You have to generate a mask to get your to select a particular region where you can deposit your silicon material. So that's what you need, a mask for a particular layer where you deposit your silicon material. That step is called mask generations. That step is called your mask generations. Once mask is generated for each layer, I mean each layer means each similar layers, then next you can go for the fabrication step, right? So let me remove it. Let me remove it. Yeah. Once it is done, the mass generation, then what you have to do, you have to go for the fabrication steps. Next step is your fabrication steps. Fabrication steps. So once fabrications you have steps, there are many steps you have to follow, many methods you have to follow. This is another topic of discussion, another subjects of discussions, and I may be introduce a bit more to the fabrication steps after going each step. And but you will detail study different type and different methods, different instruments of the fabrication steps. How the chip can be realized, how the circuit can be realized in your silicon, and all the fabrication steps, how can put the different material for the different layers. So those including your instruments and environment, that will be I will introduce at that time, and you may study all these detailed topics of these fabrication steps in your course that is called a VLSI technology. VLSI technology, which can be plotted, which generally running in our IT partner at in your eighth semester. Okay. Uh, uh, so you may go detail, but I will introduce if time permit, then I will introduce the brief about your fabrication steps, introduction your fabrication steps. Once fabrication is done, then the next step, what step is your that the your no IC will be fabricated. then the next step you have to go for the packaging. Okay, so this is fabrication steps one, what is done it. Then after that you have to go for your packaging. Okay, so packaging means that what your bare IC you have fabricated, that has to package to give the mechanical and the thermal support to connect with your physical IO pins. So okay, the packaging is nothing but that your IC, the core IC will be will be connected to your real world through through physical pins, through the physical pins. It is not only support, it gives you the physical pins, it also gives the mechanical support and also thermal support to your IC, right? So that is in the packaging part. You have to study about the pin package, and type of type of mechanical support, mechanical support or mechanical characteristics or mechanical. I can better to write the mechanical type of mechanical. Okay, type of mechanical support. Write it. I'm writing the type. So mechanical support is a, and also type of thermal support, right? So mechanical support you have to cover with a particular material, cover with a mechanical material which will give you the particular mechanical strength. Okay, that is both strength and reliability. And another thermal support means that the cooling systems, and how you will see when you will do the IC will operate, it will generate it will consume a power, and which will dissipate as a thermal energy, which will dissipate as a thermal energy, and the thermal energy has to be taken out of your chip region, so that chip will be work properly. Otherwise chip will get damaged due to the thermal energy will be associated with your circuit, right? So that heat has to be thermal energy that has to be to be dissipate in terms of heat. So in the near to heat, you should have a particular type of material which will be which will be conduct those heats and are taken out to the air and dissipate to the air from your circuit region to the air. And in addition to that, in package also, some of the companies, what they do, they will embed a small fan in your package, so that that fan will be evaporate your heat generated in this package from your IC to the package, and it will dissipate, and it will evaporate, and it will be thrown out to the air, so that the your circuit region will be get cool, that will get cool for the proper operation of your circuit. So this way the packaging is again a another topic of discussion, that is another subjects to be covered on the packaging. There is no such course is floating in our institute, but you can go through the other part of the material from the internet to study about the packaging. Packaging is a very challenging and interest topic to be covered and to know. It has a potential, potential area. It is having a potential area in the VLSI technology to study and to do the job and research on this part also in packaging. It is a challenging. It is a challenge because of the IC is getting operated. It is a huge. Millions of transistors were putting, and if you look at the workstations or servers, where it very data intensive, and it becomes the very data intensive processing units are there. So it has to be obviously it will consume say more power, and this due to this consumption of more power, it will dissipate the heat from there, and it is essential to cool down your chips and by evaporating your heats from your from the circuit part. So it is not only true that both mechanical and the thermal support, since the circuit complexity, processor complexity is increasing, so the functionality is increasing, so your pin count is increasing, right? So if you look at the today's processors, if you look at the 8085 microprocessors, it is having only 40 pins, and even if the other pins, if you look at 8 pins, 12 pins, 16 pins, like that, if you say lowest microprocessor which is having 40 pins. But now if you look at the present processors or FPGAs which has come up nowadays, those chips, they're having a more than 2000 IO pins. So it is even if it is crossing 3000 nowadays, these are IO pins. So accommodating these 3000 IO pins, you have to have a different type of pin packages. How will it take that much number of IO pins from a smaller area, smaller regions? Because chip size also, you have to keep minimum. So from minimum area, how will you put a more number of pins on that regions? So that is also beginning. That is also biggest challenge, to put the pins on particular regions, right? So the placing of your pins in a particular constraint region. So that is also a big challenge, and a lot of research is going on that pin package and mechanical support, mechanical and thermal support to Euro IC, okay, in a packaging part. So this is another topic of uh, uh, another topic to be studied. And after the packaging was it done, it obviously you have to do, whenever you do the fabrications in that core, either core or chip, or even in packaging, you have to do the finally IC testing, okay, chip testing. So next step is your chip testing. Next step is your chip testing. So you have to do the chip testing. Chip testing done, and every step, right? Every step means in the fabrication steps, and also after packaging also you have to do the testing. So that is a silicon level testing. Chip testing means that is your silicon level testing you have to perform. Silicon level testing you have to perform. Once it is done it, there are various methods chip testing you have to do it. I will also silicon testing, I will cover it, that how to do the chip testing, and what are the steps you have to take care during your design, so that you can do the chip testing easily after the fabrications. So that part, that step, that is called a DFT. DFT basically, that will be done after your in your design step, that is called DFT. And the DFT is nothing but your minute. DFT, the we will study the DFT. I will introduce the DFT, that is called a design for testability. Design for testability. Okay, so this is a topic I will introduce to you either in the at the end of the design step, or before going to the fabrication steps. So on that part, it comes actually. In design steps, so there how you will take care efficiently to test your chip. That concepts, basic concept, I will introduce sometimes. That is called your design for testability. So I think this is all about your full custom design steps. Broadly, what I spoke now. So now, what you do, like so these are the all steps for the full custom design, right? So that is specifications. Then you have to choose. I'm repeating very quickly. So you have to find, you have to go with to reach the specifications. Then you have to go for the circuit topology. Circuit topology. Then you have to go with your circuit simulation. Then physical layout design. Then you have to go with the physical verifications. then integration with the IOPAD, then you have to go with the chip level verifications, then you have to tape out your chip, that is you have to generate your GDS2. Then after that, this is called your full custom design step, and after that you have to go to the fabrication step, that is called your that is called your get your GDS2 for your design team. Then you go for the mask generation step. Once you generate your mask, then you have to go to the fabrication steps. Fabrication steps means that putting the silicon material per particular layer on wafer. Then you go to the packaging. Then you have to go for the chip testing. Once it is done, then you have to go for the no employment deployment of your chip in your application. Deployment of your deployment of your chip for a particular applications, or you have to get into your market. Okay, you have to sell out in your market depending upon the chip you have designed. So these are all the steps you have to go with the full custom design. So why it is called a full custom design? As you know as I was discussing yesterday, you have to customize your specifications. I mean, you have to fulfill your you have to fulfill your all the desired specifications. So each and every steps you have to take care so that it is meeting to your desired specifications. Suppose you want to have your area of area specification is say 20 mm². So area of the chip 20 mm², then you have to have your 20 mm². Suppose it should be operate at a speed of say 100 megahertz, then it has to work. You have to design such that it has to be satisfied and it has to be operate at 100 megahertz. Suppose similar to the power, it should be say maximum power consumption should be say, suppose I say 2 milliwatt, then your power, it has to be maximum power should be within the 2 milliwatt. So you have to design such that then that should be at the the maximum power should be within your 2 milliwatt. The power consumption should be within the 2 milliwatt, right? It should be satisfied. No, I mean, you are customizing your design such that it should be fully satisfy your desired specification. That's why it is called a full custom. Means full custom, each layer, each level you have to consider so that it has to be it has to satisfy your what is the resultant outputs you will get. It should be it should satisfy fully to your design specifications. That's why it is called a full custom design approach. You are customizing fully to your design specifications. Okay, so this is called a full custom steps. So full custom design method. So let's, once we done it, then next to what you will do that say the first step. I'm not going to a particular specification, particular applications. In the beginning we will go with a very generic circuit, generic topology each step. Then next we will go to the to the very particular applications, or how to do the analysis for that. So so you will study the circuit topology. So first step is your circuit topology. Okay, so first step is your circuit topology. Let's will go with the circuit topology first, then you will go to the physical layout design. So first step, we will go to the circuit design, or select your topology, circuit topology. You can set circuit topology. Okay, so in this circuit design and topology, we will go with the very basic circuit. Say for example, your functions to get your inverter, right? Suppose you want to get your inputs like this, and output will be your say like this, right? Okay, so sorry, yeah. So circuit will be, so input is that this and output functionality is like that. So this is nothing but you are inverting your input and you are getting the inverted output. So you will get that circuit. You will get a block diagram. If you look at the block diagram, so it should be a, sorry, let me get a black box of that one. So it is your input. Okay, this is your output. So you will get the, this is your, it should be a circuit. So let's let what should be this black box, what should be a circuit, this is black box. So okay, so looking at the behavior of your input and output, it is obvious that it is a functionality is a inverter. It is a inverter. Okay, the functionality is a inverting nature. So the functionality is your inverter. So once it is done your inverter, then so I mean you can say that in the schematic view of this one, you can take into the schematic view of this one. So this is your inverter, right? You know this is your input and this is your output. So this is your inverter. Or maybe say for example we will go with a so you know all these things, but I'm repeating once again uh, uh, the completeness of your this full custom, the what is the how the steps you will follow for the full custom. Say for example say I will have a input up like this, and out, this is your input, and output behavior is also like this. Okay, I will like this. So this is nothing but the input is same as your output, but having some delay. Okay, having some delay, right? Having some delay, or may not be delay will be there also. Maybe small delay will be there. So here the means input and output remains same. Means output is not getting inverted. So it is a simply a buffer. It will which will provide a simple some delay. So the topology, if you look at the block diagram descriptions. So suppose this is your uh, input, and this is your output. This is your output. Then in input to the output, the behavior looks like that. It is not getting anything. The input is passing as a output with a small delay. So it is, I can say this is your buffer. Okay, just it is buffering. So it is not doing any manipulation, just it is getting delayed, and input is will go to the output as it with a some delay. So that functionality is your buffer. So buffer, you can schematic view can look at, this is your buffer. So this is your input and this is your output. This is your schematic view. When the circuit point of view, it is represented as a buffer, represented as a triangular form, right? So whether it is an inverter or buffer, so then you have to, next step you have to go to have your circuit part, and which is maybe a logical circuit, or it can be a transistor level circuit, right? So then let's will go directly to the transistor level circuit, because this is of course now if you look at the logical component, of course this is you are representing, this is an inverter, it is a logical inverter. This is your logical inverter. This is your logical inverter. If you look at the digital point of view, digital signal point of view, or if you look at the analog point of view, so it will be an analog inverter. it may be implemented using your OPAM or other circuits. So if you look at the logical inverter or digital inverter, then schematic view is like this. And if you look at the digital buffer, the schematic, it looks like this. So now this logical schematics, then you will go to the our transistor level schematic. So if you look at the inverter circuit, so in inverter circuit, if you look at the inverter circuit, then you will find that different topologies you will get it. If you look at to the different circuit topologies, if you look at the circuit topology, right? So then you will get a NMOS inverter. Then you will get your PMOS inverter. Then you will get your CMOS inverter. Means this topology depends upon that what type of devices you are using, whether you are using NMOS inverter or PMOS inverter or CMOS inverter. Okay, NMOS inverter, PMOS inverter or CMOS inverter. If you come to the NMOS inverter, so NMOS inverter, so if you look at the NMOS inverter, this is active load inverter. Okay, active load inverter, passive load, that is called a passive load NMOS inverter, which is called the topology. It is look like topology is looks like topology is look like VDD and ground, and you will have your NMOS where you will get your input, and you will get your register, load register. This is called your driver, and this is called your load. So load will be your register, and you can get your output. Okay, this is called a passive load NMOS inverter. So how it works? Like if it is a input is a 0, if an input is a 0, right? So means that NMOS will go to the off, right? NMOS will go to the off. So off means that the output will be tied to your VDD. So you will get output is 0, 1. Okay, output is 0, 1. And similarly, if you give your NMOS equal to 1, input is 0, 1, then your MOSFET will be go to the on saturation state, and it will go to the on. Then output will be tied to your ground, so that you will get your 0. I means whenever you will get a 0, output will be your 1. And if you will give the input as a 1, then output will be your 0. So this is your passive load NMOS inverter. Passive load NMOS inverter. Okay, and similarly, you can get your active load active load uh, active active load NMOS inverter. NMOS inverter. So in active load NMOS inverter, uh, active load NMOS topology is like this, that instead of register like passive component, you have to put with the active component. You have to replace with the active component. So means that active component should be the NMOS type, right? So in that case, so the topology will be like this. This is your VDD, and this is your ground, right? And the driver side is your input. You have to give it, that is a NMOS type, and the load will be active. So the register you can replace with a NMOS device, and which can be operated at the saturation regions. So if you connect gate and source, then it will be your active register. So I mean that passive register is replaced with your active register. The active register, active load means that active register can be realized use your NMOS using your connections that get, if you get and source will be shorted. So then this becomes your active register. This is nothing but your active register. Okay, this is nothing but your active register. So instead of passive register, you have to get your active register and realize your you can realize using your NMOS device. So since both NMOS devices are there, so fabrication will be easier than compared to your passive register, right? So this way you can get your output from here. This is your output. So the advantage of the placing your active register with your NMOS devices compared to your passive register, that your fabrication process will be minimized, because while you are realizing your this driver MOSFETs, the active MOSFET, that load MOSFETs also you can realize in the same time. Only the additional connections you have to taken care, that the gate and the source has to be connected by the additional process of the metallizations. That one metal connection, one metallization process, you have to add it in this in this process. So that way if you go with the passive component, that passive component you have to go with the a particular passive component will take a larger area. Also passive register will take a larger area compared to your active register, and it will also take a lot more time to fabrications compared to active register. So I mean active register is realizing the active register is nothing but you are minimizing the fabrication steps. It will minimize the time. It will be it will take the less area, and so that cost will be also minimized, right? And your area will be minimized. Okay, so this way it will be advantage if you go to the active low NMOS inverter. So today we will stop here, and I will talk more on the other topologies tomorrow. Okay, if you have any doubts, I can take up. Otherwise, we will end the meeting.
Sir, in the first class you mentioned you will tell us the books that you'll be
Okay, yeah.
referencing.
Thanks for your remind. Since I am started the topics, so tomorrow I will describe. Okay, now also let me brief you what I will topic now. Covering the topic, I will give the all the books, but today what we will discuss. You follow the basic VLSI design book. Just take out basic VLSI design. Okay, or introduction to VLSI design, that is you check it by Pocknell. Okay, by Pocknell, or you can look at another similar book, introduction to VLSI design, or you type it into basic VLSI design or introduction to VLSI Pocknell, or that is also another book in this title. You will get your by OLF. Okay, there are Pocknell is a author and Wolf is another author. They have books of basic VLSI design or introduction to VLSI design. You can read either of one book, and second, which is circuit part, what I will cover it. That is a CMOS circuit circuit simulation and circuit simulation and layout by uh, uh, by that is called a three authors, Lee, Boyce, and Becker. Okay, Lee, Boyce, and Becker. But these are all old editions. But a new edition of this book is only Becker. This same title with the only Becker. Okay, so which edition you will get from your internet source, that is good. I think new edition also you will get downloaded from your book. It is available in the internet. You can download the CMOS circuit simulation and layout by Becker. So I am sure whether you will go with those Wolf and Bucknell books, but I will suggest you to download this CMOS circuit simulation layout by Becker. Okay, so your latest version, it is also available in PDF format. You can freely available. You can download and you can go through it. And I will cover the most of the topics from this topic before the mid-sem, till the mid-sem. Okay, and other books also I will introduce in due course of the time. Thank you.